The dynamic CMOS logic, Precharge-Evaluate logic. In the following, we will introduce a dynamic CMOS circuit technique which allows us to significantly reduce the number of transistors used to implement any logic function. The circuit operation is based on first precharging the output node capacitance and subsequently evaluating the output level according to the applied inputs. Both of these operations are scheduled by a single clock signal which drives one NMOS and one PMOS transistor in each dynamic stage. A dynamic CMOS logic gate which implements the function f equal to a1 a2 a3 plus b1 b2 is shown in figure. When the clock signal is low, precharge phase, the PMOS precharge transistor MP is conducting while the complementary NMOS transistor ME is off. The parasitic output capacitance of the circuit is charged up through the conducting PMOS transistor to a logic high level of Vout equal to VDD. The input voltages are also applied during this phase, but they have no influence yet upon the output level since ME is turned off. When the clock signal becomes high, evaluate phase, the precharge transistor MP turns off and ME turns on. The output node voltage may now remain at the logic level high or drop to a logic low depending on the input voltage levels. If the input signal create a conducting path between the output node and the ground, the output capacitance will discharge towards VOL equal to 0 volts. The final discharged output level depends on the time span of the evaluation phase. Otherwise, Vout remains at VDD. The operation of the single stage dynamic CMOS logic gate is quite straightforward for practical multi-stage applications. However, the dynamic CMOS gate presents a significant problem. To examine this fundamental limitation, consider the two-stage cascaded structure shown in figure. Here, the output of the first dynamic CMOS stage drives one of the inputs of the second dynamic CMOS stage, which is assumed to be a two-input NAND gate for simplicity. During the precharge phase, both output voltages Vout1 and Vout2 are pulled up by the respective PMOS precharge devices. Also, the external inputs are applied during this phase. The input variables of the first stage are assumed to be such that the output Vout1 will drop to logic 0 during the evaluation phase. On the other hand, the external input of the second stage NAND2 gate is assumed to be logic 1 as shown in figure. When the evaluation phase begins, the output voltages Vout1 and Vout2 are logic high. The output of the first stage Vout1 eventually drops to its correct logic level after a certain time delay. However, since the evaluation in the second stage is done concurrently starting with high value of Vout1 at the beginning of in this figure, you can see illustration of cascading problem in dynamic CMOS logic. The evaluation phase, the output voltage Vout at the end of the evaluation phase will be erroneously low, although the first stage output subsequently assumes its correct output value once the stored charge is drained. The correction of the second stage output is not possible. His example illustrates that the dynamic CMOS logic stages are driven by the same clock signal cannot be cascaded directly. His reverse limitation seems to be undermine all the time advantages of the dynamic CMOS logic, such as low power dissipation, large noise margins, and low transistor count. Alternative clocking schemes and circuit structures must be developed to overcome this problem. In fact, the search for viable circuit alternatives has spawned a large array of high-performance dynamic CMOS circuit techniques, some of which will be examined in the following session. Thank you.